Okay, so if you look at microscopic organisms swimming, the reason why they swim quite often is they have these flagella or cilia that can just kind of wobble, and as a result of that you get propulsion, and as a result of that you get a motile particle or a self-propelling object. So, and now the question you can ask yourself is, why do they do this? Why do they swim? And if I would stir the mixture, why do they swim at all? If I could just shake it, then there's no need for swimming, maybe. So, and then again, you're at different length scales. So stirring on a macroscopic scale moves stuff around, but stirring on a microscopic scale doesn't move anything around. So if you transform yourself to an object that is 1 micrometer, then local stirring doesn't do anything to you. So if you think about that, so let's look at some scaling laws. So you have the time to move by stirring. Is basically the distance you would like to travel, L, divided by your speed, V. Yeah? The time for transport by diffusion, Brownian motion, for example, is L squared divided by D. Now, stirring works is L times V over D is greater than 1. Otherwise, so if you take the ratio of these things, if that's smaller than 1, stirring doesn't work anymore, because diffusion is faster than stirring. So that ratio is basically called the Peclet number. In the paper by Purcell, he forgot what it was called, so he just calls it S in this particular case. And he even says it's probably called some dimensionless number. And so it's either the Peclet number or the Brenner number. It's basically the same thing as S, which is length times velocity divided by diffusion coefficient. So what we're trying to say is that stirring only works on a macroscopic scale. If you slow stuff down, or if you shrink stuff down, then stirring doesn't really matter anymore. So diffusion is important. So if diffusion from the stuff around you is important, you could argue that as a bacteria, as an E. coli, you would like to swim, because maybe you could eat more. Yeah? So if there's lots of things that you can eat around you, then maybe this is a reason why you want to swim. So let's have a look at that on the left. So the little dots are nutrients, and then you have a certain food supply, and you're a spherical object in this case. And we've seen this equation before, actually. So the rate of collision, molecules per second, we come back to later, is Smoluchowski, which was, go back all the way to entry of a monomer droplet, of a monomer molecule into a latex particle. Yeah? So for food supply, the rate of that is 4 times pi times the radius of the object times the number times a number of Avogadro times the diffusion coefficient of the molecules. Now, that's for an object that moves through Brownian motion. So maybe if you want to eat more and grow a bit better, you want to swim. So would that actually work? So, and then you can calculate that to increase your food consumption by 10%, you have to swim, in this particular case, at 700 micrometers per second. Unfortunately, bacteria don't do that. So if you pick a bacteria that's about 1 micrometer, 2 micrometer, an E. coli, they can swim up to 20, 30 micrometers per second. So we're a factor of 10 off. So the reason why they swim is not because they can snap up more food. That's the wrong answer. So let's look at a different argument. So why would they swim? So maybe they just want to outswim diffusion. Yeah? So if you can swim faster than stuff would spread by self-diffusion, you can explore unexplored territory. Yeah? So if I would be in a very small, and I would be in a swimming pool, and someone put some ink in there, and it's blue, and I want to go to a region where there's no ink, the ink spreads. I need to be able to swim faster than the ink spreads, so I can stay ahead of it. Yeah, which means I can explore new territory. So you can think of the other way. I'm in an environment and I've eaten a lot, and if I swim faster than stuff diffuses back in, then I can explore areas where there's on average more food. So maybe that's the reason why I want to go there. So, and in order to do that, the length of diffusion, that L needs to be, well, d over v, the same equation, that needs to be greater. So basically, if the diffusion coefficient would be 10 minus 5 square centimeters per second, which is roughly the self-diffusion coefficient for any small molecule, in this case water, and v would be the speed of this of an E. coli, for example, 30 microns per second, yeah, then L needs to be greater or equal roughly than 30 microns, and that roughly adds up. You don't really have to swim that far. So if you can swim at those speeds, then you can beat the diffusion of molecules, which means you can find molecular nutrients, which could be the reason why you want to swim. So if you want to know more about this, then you know, you should have a look at and read the paper. So here, I want to kind of give you an idea on how crazy you can go in a bit when you're going to try to design your own little machine. So in this particular case, which was published in Nature quite a few years back actually, in 2005 already. So they had a blood cell, a red blood cell, and to the red blood cell, they attached a bunch of magnetic particles that were linked together with DNA chains. And the reason why they were covalently, well, not almost covalently, well, strongly attached to the particles was because of a biotin-streptavidin interaction, which is a very, very, very strong association constant. So in a way, you kind of make a train of these kind of things. And what people did then is that you've got these train of these magnetic nanoparticles interlinked together, which you attach to this blood cell. And they, in this case, they cheated a bit. They applied an external magnetic field. And then they were able basically to make a hybrid between a real cell and give it a flagella in a way, which is this wobbly bit at the end. And then, so on the right hand side, you see a snapshot on how this thing actually should swim. And I think this little movie clip shows you that it actually can swim. So that's what it does. And it's a periodic kind of movement, and via this way, the thing just propels itself forward. So the question now is, you know, if you would have an object, or if you could make an object, and you want it to move, you can't use steering, yeah, because it doesn't work on this length scale. You can give it an engine, like this, for example. So you can give it a flagella, or you can give it another external field gradient. You know, we've seen before that a soap boat would work, for example, by inducing a gradient in surface tension. So what kind of crazy chemistry and physics could you come up with in the next 10 minutes to make something like this? Okay? All right. So have a chat with each other, and after that we'll see what's possible and what's not possible.